A couple of times in this course, we've talked about the arrival of a sort of miracle material, porcelain in ancient Rome, or fired brick that has a sudden increase in compressive strength, material that sort of changes the game and makes builders, engineers, architects think of what they're doing in a new way, gives them new opportunities, and sometimes forces them into thinking of new ways of figuring things out, both how to build and how to estimate how the structure itself is working. Today we're going to talk about probably the biggest leap that we make, which is to go from kind of brick and timber and stone, all of which we've seen in use for 3,000 years or so at this point, to a new material, one that has been used before but not as a constructive system. And the appearance of first cast and wrought iron and then later steel is something that really defines the kind of edge between ancient, or at least kind of medieval and Renaissance construction, and what we would think of as really modern construction today. What I want to do in this lecture is go through both the kind of material development of iron. We've seen it in use before a couple of times, but on a very small scale. Look at a paradigm example of how the new material influences a new type of construction, mill construction, mostly in Great Britain, but also coming over to North America. We'll look at cast iron facades, which are one outgrowth of mill construction. And we'll look at long span as a functional response. In other words, what happens when, for the first time, you can take a lightweight structure, not a masonry vault or masonry shell, and equal some of the same spans that ancient Romans or Gothic builders were achieving, but in a material that is much lighter, puts less stress on the foundations, and is built in a very different way. We'll look then at steel, the difference between cast and wrought iron and steel, and then how steel in particular allows for this one type, the long span train shed, to emerge, that because the material is on the one hand providing the kind of functional spur, the locomotive and the railroad, and also the constructive means of achieving that function, we get this really kind of tight integration between the way things work, the way they're built, and the material kind of in between that goes between them. So to start with, whenever we've seen a new material, we've always backed up and we've looked at its material properties. And for a couple thousand years, we're basically talking about two types of iron. Cast iron, in which iron ore is literally just melted, poured into molds, and used in a building type, or in a building or construction area. Cast iron is very strong in compression. You can see 6,000 to 8,000 kilograms per centimeter squared of strength, but it's weak and unreliable in tension. It is subject to all sorts of imperfections like entrained air bubbles, things like that mean that the section isn't really reliable. You never know quite how much cast iron you've got. In compression, that's fine. If you squeeze an air bubble out of a cast iron column, the iron will come to rest on itself, and you may never know that the bubble popped. If, on the other hand, you've got a bubble in a tensile element, when you apply more load than the resulting section can take, obviously what's going to happen is the column or the tensile element's going to fail, and it's going to fail catastrophically. So the trade-off in cast iron is that it's extremely strong in compression, but actually dangerous in tension. It's also very difficult to work. Once it comes out of the mold, because of the high carbon content, it's tough, so it's hard to drill or cut or slice, but it also has an unfortunate tendency to fracture when you try to slice it or cut it or drill it. This means it can't be used on the job site, right? You can't rivet a piece of cast iron because you may be standing on it and it may shatter and drop you. But it also means that it's very, very hard to get any sort of precision in the connections. What comes out of the mold is what you get. And that piece, as it's cooling, may twist or it may shrink in ways that are a little bit unpredictable. So there's some drawbacks to that very, very high compressive strength. Wrought iron, on the other hand, is iron that's been puddled. In other words, they melt the same iron ore, but then they literally scoop out the carbon deposits that form on the skin of the molten iron. And what this means when you take the carbon out is that you lessen its compressive strength by about 50%. But you also get a reliable tensile strength. So wrought iron is the first material really that we can use in tension. We've seen a little bit of that in the chains in the dome at St. Peter. And most importantly, it is ductile. It can be worked, you can drill into it, you can make very, very precise connections with it. You lose a bit in compressive strength, and it's expensive because you have to actually pay people to take the carbon deposits out of the molten iron, but it's more versatile. It can be used in other situations. No spoiler alert here, but you can see where we're going, right? What you would really like as a metal building engineer is a metal that is equally strong in compression and tension, but that is also ductile or workable. And we'll see steel emerge as this kind of magic form of a material that's already kind of a magic construction material. And just to make the point, we can go back and forth and look at these, but steel doesn't really, we don't think of it as having a hardness like we do in stone, but look at the difference in the compressive strengths of stone. These are all the Roman examples that we looked at. Basalt, for instance, which comes out of the volcanoes near Monte Albani or imported from Egypt, that can get you a compressive strength of up to maybe 3,000 kilograms per centimeter. That is the only material that even comes close to the compressive strength that you get in wrought iron, much less cast iron. And then look at the tensile strength, 2,800 to 3,700 kilograms per centimeter in wrought iron, and you can see that we're nowhere clear. We're orders of magnitude weaker when we're building in stone. So obviously the implications are going to be profound. We have a material that can do all of these new things, and it's going to solve a lot of problems that human builders have been trying to solve for centuries, in some cases millennia. So iron is around for a while. We've seen iron used in cramps, for example, in Greek construction. And like I said, we've seen it used as chains in St. Peter's. But it was essentially a kind of precious metal until the late Middle Ages, a material that was used often for weaponry, swords, things like that, but not so much for building construction. The first blast furnaces, which we'll talk about for a little bit, this is the crucial method that allows iron to be commercially produced, come around in the 14th century in Northern Europe. We'll talk about why that is here in a second. But the real improvement comes in Britain in the early 18th century when Abraham Darby develops a process that melts the iron using coke or rarefied coal. And what this does is it actually adds carbon to the mix. So it makes it very hard to work, but it makes it very, very, very strong. And Darby's experiments with cast iron are really the things that kind of open the floodgates to metal construction in Great Britain, at least. It's mostly a casting process, so while you need some skilled labor, you no longer need an army of blacksmiths hand-making building components. You have the ability to do it, a sort of rudimentary form of mass production using the casting. And once Watt invents the steam engine, which itself comes out of the ability to make machine parts out of iron, there are tools that allow more mass production. So you can automate the process to some extent. You can have machines that pour the molten iron, that stamp the iron, that get it out of its molds. And by the 1780s, iron construction is really a mass-produced process in a lot of ways. Wrought iron, on the other hand, takes a little bit longer. It's a fussier process to refine the carbon out of iron ore. But by 1830 or so, we get not only improved methods of doing that, but we get better methods of actually working the result. Rolling processes in particular, what we're used to seeing now when we make steel members, first come about in the 1830s with wrought iron instead of steel. And wrought iron especially gets a lot of scientific treatment because it can take tension, because it seems to be very, very good for beams and spanning elements. A number of engineers, especially William Fairbairn, begin scientific experiments on wrought iron in the 1830s and 1840s that really give us what today we think of as our method of designing steel beams, right, involving strength of materials, neutral axis, section modulus, and the flexure formula. So, okay, how do you actually do this? Well, the key thing to refining iron is what's called a blast furnace. This creates an interior that's very, very hot, and it moves a lot of air through the molten iron. iron ore and coal usually put in at the top of the furnace, often with some limestone, which helps take the impurities out. The furnace is lit on fire, so the coal is burning along with the iron ore. And what happens is that gradually the molten iron drops to the base of the furnace and can literally get tapped out of the bottom. On top of the molten iron is a layer that's called slag, which is mostly impurities. And then what goes on top of that ends up being the ash from the coal that burns. So it's taking advantage of the fact that all of these things act basically as a fluid once they get hot enough. And iron being heaviest, it sinks to the bottom where you can tap it off and get raw molten iron or pig iron. And we have examples of these in Europe. Certainly, this is one that would have been maybe like that one in Belgium in the 14th century. You can see that it's pumping air into the furnace by use of a water wheel. So Roman technology revived in medieval times and being applied to a process that's going to take us another step further. But this is a process that we see around the world. This is an early medieval Chinese manuscript that shows exactly the same process, a bellows that is pumping air into a very, very hot fire, and that bellows is powered again by a water wheel. So the iron process itself, even though we think of it sometimes as handmade by blacksmiths, there are ways of producing at least the ore that are largely mechanized by the 14th, 15th century. Wrought iron, on the other hand, does not have this kind of industrial scale because it relies largely on the actual labor of humans to take the carbon out of puddles of molten iron. The process is called puddling. The other way to do this is by hammering red-hot wrought iron and literally hammering the carbon out of it. Either one of these are intense, labor-intense processes. They are unpleasant and dangerous. You can imagine what the room on the left, where these guys are scooping the carbon out of the furnace, you can imagine just how hot that is and how unpleasant and how easy it would be to get burned or to lose your life in a situation like that. As a result, wrought iron, you pay for the flexibility and the agility of the material. It comes out in relatively small quantities, and it requires an awful lot of effort to get that kind of magic balance between tension and compression. The advantage to wrought iron, though, is that it's ductile, and you don't need to melt it to make a new component. You can heat it up so that it's red hot but not molten, and you can run it through a series of hardened iron rollers to gradually take what's called a billet of wrought iron, a long sort of stick of wrought iron, and shape it into whatever extruded shape that you like. As long as you can make it with these rollers, you can make a kind of infinite amount of wrought iron stuff. On the upper right and lower right, you see the process for making railroad iron. And if you look, the rollers, what this guy on the left is doing, he's drawing the bar through one roller and shoving it back through another. And gradually that billet of iron is going to go from a pure rectangle to, as you can see on the right, something that's beginning to resemble a piece of railroad iron. A hot process for sure, one that again relies on this poor guy standing with the super hot piece of wrought iron, but also one that's very amenable to mass production, that especially after the steam engine comes in, rolling mills can use steam power to drive a lot of the process of shaping these elements of wrought iron. Now, why this happens in Belgium and England instead of in southern Italy, where we've seen most of the developments in building technology, relies entirely on the geology of Europe. On the left, you see the location of iron ore, in other words, where you get the raw material. And you can see that most of the iron ore in Europe comes from this small area on the border between France and Germany, a little bit in the north of England, and you notice like almost none throughout southern Europe, which is one of the reasons that southern Europe stays with stone construction and in the 20th century adopts concrete so quickly, because they don't have access to the ore that the northern half of Europe has. And on the right, you can see the other key ingredient where the coal is in Europe. And coal we think of as being concentrated heavily in Great Britain, which certainly is. But you see there's also this kind of vein of coal in Belgium, Holland, northern Germany. And these two become the kind of centers of iron production and therefore of iron manufacture and of iron construction throughout the late 18th and early 19th century. Now, again, we've seen this before. We've seen iron used by hand, basically replacing the wooden dovetails in Egyptian construction with iron or sometimes bronze that clamps blocks together in Greek construction. You may remember the trick here is putting the clamps in either molten or at least very, very hot, so that as they cool, they actually draw the stones together and form a tight bond. So iron's certainly known about, it's certainly used, but look at the scale that it's being used at here, right? This is artisanal production of iron, blacksmiths laboring over very, very small, kind of delicate pieces that are used very sparingly, right? This is not a building system, this is a building component. We get a little bit closer to systematic construction in the east facade of the Louvre by Perrault, which we looked at yesterday, or in the last lecture. Reinforced masonry, basically, so stone that's relying, again, on probably artisanally produced bits of blacksmithed iron to hold it together, but nevertheless a kind of expansion, more complex shapes, and used in a wider variety of applications than in Greece. And interestingly enough, it's Christopher Wren who kind of pushes wrought iron especially into becoming a construction material. This is a library that he does for Trinity College in the late 1700s, and all of those heavy books are sitting on a relatively lightweight floor that, as you can see, is supported by concealed wrought iron rods that run from the masonry walls down to the floor, holding up the floor, disguised though in the bookcases. Similar situation here to St. Paul's, where we talked about the fact that the vaults of the nave in St. Paul's are hidden. Wren builds these gigantic parapet walls, almost as if he's embarrassed about the flying buttresses. And here he's really after the kind of rectangular order of the space in the library. And so the wrought iron, even though it's a really innovative use of the material, is nowhere to be seen. Right, all you see are the books. Now he also uses it in the Sheldonian Theatre, this theatre that he designs at Oxford for the columns. Those are cast iron columns that are holding up the balcony. And a little bit later, the now demolished House of Commons in London. And in both cases, the important thing, just like the churches that he and Hooke designed throughout the City of London, the important thing is to get the columns as small as possible so that they restrict views as little as possible. And cast iron is perfect for this because it's so much stronger than brick, so much stronger than stone. You can support the same load with a much, much smaller cross section. Now, Abram Darby is the one that we normally credit with this coke process of producing iron. And he's also a kind of blacksmith on an industrial scale. And he creates, along with a couple of other builder engineers, this sort of proof of concept of iron construction in 1777. Colebrook, as you can imagine, is in the north of England, in an area rich with veins of coal and coke. Darby provides the mass-produced iron for this bridge. Pritchard and Wilkinson basically are what we would think of today as the engineers, right? Designing both the structure and thinking about the way to build it. It's not a particularly sophisticated structure, right? It's a semicircular arch, and we know by this point that what you really want is a catenary arch or something more of a parabola. But nevertheless, this is proof of concept, if not of a really innovative structure, of a really innovative building system. The whole bridge is made out of iron. All of the struts, all of the structural elements are made of cast iron. You can see that they're repetitive, so Darby sets up one mold and uses that mold again and again and again to create the same element over and over. That's one of the reasons for the semicircular arch. He can work to a consistent radius and use the same jigs again and again. And you can see too that it is a pretty impressive span, and it achieves that span because it doesn't have the dead weight that a masonry arch would have. It only has to carry its own relatively light weight, the weight of the iron arches, instead of the heavy weight of the masonry. And as a result, the bridge is able to span with much less material, which puts less stress on the foundations, among other things. Now, how does this get transformed into a system, right? What do we mean by a system? Well, the iron itself, we've seen mostly as components. Colebrook Bridge is the first place where someone says, how far can we go? How much can we use iron in the construction of a bridge? And about the same time, the invention of the steam engine, the sort of adoption of industrial processes, in some cases, the production of iron itself, leads to a new type of factory that gets called a mill. Mill construction has come down to us as a word usually meaning like heavy timber or post and beam, but it's a very, very specific type of factory in Britain in the late 18th century. Multi-story factories built out of timber had been common. Timber is plentiful, it's easy to use, relatively quick to assemble. But with steam boilers and especially things like furnaces, timber ends up being, of course, a very bad material to use because it catches on fire. And mills in Great Britain had an appalling safety record. They went up in flames all the time and killed lots and lots of workers when they did. So the idea of using iron, which has a reputation as quote-unquote fireproof, it's not quite fireproof, but it's certainly more fire-resistant than timber, starts as early as the 1790s. We'll look at a couple of these early examples by William Strutt and others that try to take the iron that's coming out of places like Derby's mill and extend it to take up most of the building structure. Initially, these are hybrid structures, so iron columns which take up less floor space, and then timber beams that span usually to brick walls. The brick skin is typically what's giving the structure its lateral stability. They're load-bearing brick walls, but they also do most of the wind bracing. And then gradually, as builders get more and more familiar with iron, we see the iron kind of migrate into the girders and the beams. And then in a kind of great leap that takes place in mostly North America rather than Great Britain, we'll see that iron structure actually emerge on the skin as well, right? So the buildings end up being built entirely almost of one material. So here is Strutt's mill, and you can see that it's got a brick skin. It has a very, very light set of columns in between. If you look at the floor plan, you can imagine that you could move looms or machinery, spinning wheels all around the floor, right? The structure doesn't take up a whole lot of space. You can see that there are brick floor arches that frame into timber girders, right, that span the short distance between the brick walls and the cast iron columns between. Also note that is 6 stories in the 18th century, which is an immensely tall building for a multi-story building. These are like the Roman insula, right? They're about that tall. All stairs, of course, no elevators for the workers. But notice the proportions of the column, right? And how skinny those are, how little floor space they take up. This is the crucial advantage, right? Build one building and basically be able to use much more of it because the columns are so small. Now, Strutt's mill is the one at the top. You can see that there's a cast iron column that holds up a timber beam. That timber beam has these little kind of sideburns of wood nailed onto it that are going to accept the springing point of the brick floor arches. So very, very shallow brick arches that form the flooring for the next level up. And the need to give those brick arches something to push against, right? Something to absorb the thrust that they're going to put onto the beam. Now, when a few years later in Shrewsbury, Benson and Bage build a mill, they take the next step and they say, well, what if we made the beams out of cast iron as well, right? Okay, now we know that cast iron is lousy for beams because it's unreliable in tension. But in the late 18th century, this is kind of what they got, right? Too expensive probably to do wrought iron, and so cast iron is going to be what it is. Well, you can see where the column fits in, and you can see that, first of all, it takes much, much less cross-section to carry the load than the mill at Milford. But also notice that they have to keep the little triangle on the base. They still need that geometrical shape to accept the bottom of the brick arch and to take this thrust of the brick arch into the girder itself. Now, as they build these, builders start to realize that little triangle, or just even a little tab, as you see in the mills at Salford and Leeds, that little tab that initially starts as a way to accept the thrust of the brick floor arches, also has a structural function. And it's not an intentional one at first, but it's one that gradually emerges, that gets gradually recognized. Builders realize that all of these beams are much, much stronger than if the same cross-sectional area had been deployed in a simple rectangle. And today we know the reason for this, right? These are actually kind of rudimentary flanges that are starting to give those beam shapes a much, much greater moment of inertia and much greater section modulus, because they're increasing the kind of the average distance of each little piece of steel from its neutral axis. As you put more and more material on the top and bottom, you're giving that beam a greater resisting moment arm to resist a load that's being put on it at its center. These, of course, aren't terribly efficient, right? They don't look very much like today's W shapes. They've just got these teeny tiny flanges. But builders start to realize, and building scientists start to realize, that the larger those flanges are, or to put it more accurately, the more of the section's material that ends up in the flange instead of the web, the more effective and the more efficient these beams get. Now, there's some other kind of interesting quirks that I find really fascinating as builders and building scientists are trying to figure their way basically to the I-beam. There is a whole series of mills that takes advantage of the casting process to make what are called fish belly beams. Here you can see that the longitudinal section looks exactly like the combination of a shear moment diagram that you all are used to from structures classes. It's really, really deep in the middle where the bending moment is greatest. The shape of the beam follows roughly the curve of the moment diagram, so it's actually decreasing as it gets toward the ends. But then at the ends, the engineers realize that they need enough cross-sectional area to handle the shear, to keep the beam from just punching past its columns. So the fish belly beam, you can't make this in wrought iron. You can't roll that shape, right? A rolled shape has to be purely extruded. But in cast iron, you can make whatever crazy shape you want. And they get to the point where they are actually building efficient shapes longitudinally, right? Taking advantage of the emerging science of that shear and moment diagram to build a beam where the material is deployed exactly where it needs to be. Now, the other cool thing about this one is look at the cross section, right? AA and BB. They are starting to realize that the I-beam, right? Today's W shape, the flange and web combination is the secret to making iron beams that work really, really efficiently. Right? Put a flange on the top and the bottom of the beam. You draw the resisting moment out to the greatest moment arm you possibly can. Increase that moment of inertia, increase that section modulus, and pretty soon you have a really modern I-beam. Here are those fish belly beams in practice. Cast iron columns, cast iron girders, cast iron beams. You get a sense for the kind of clumsiness of the connections, right? That these are not ever going to be rigid connections because of the imprecision of cast iron, and all of that masonry around the outside is what's going to give the building its lateral resistance. And here you can see really, really long span cast iron beams. These function basically almost like double cantilevers, right? They're supported minimally by the brick at the ends, but they're also, most of their load is taken up by the cast iron columns in the middle. And you can see that these go up again 6 or 7 stories very, very easily. The weight of the structure, the dead weight of the structure, is much, much less because of those lighter weight, smaller cast iron columns over, say, brick piers. Now, wrought iron comes into play too in interesting ways, and because builders know that wrought iron is more reliable in tension than cast iron, you get really interesting hybrids, like this beam that's used in the old Charing Cross Hospital in 1830. What's going on here, if you look at the longitudinal elevation, you can see that Burton is taking advantage of the shear moment diagram principle, right? The beam is thicker in the middle than it is at the ends. You can see that Burton knows about the neutral axis, knows that material near the neutral axis is lazy, and so he's cut that out, or rather molded it out, right? Used a mold that excludes material from those big openings. And then finally, look at the cross section. This is a cast iron beam that forms the longitudinal shape, but it rests on a wrought iron bar that runs across the bottom of the beam, right where the beam is experiencing the greatest amount of tension. So wrought iron is taking the tensile forces in the bending element, cast iron is taking the compressive forces, and they know that this is where these two materials belong, right? This is an example where they're actually working in tandem, right? A hybrid cast and wrought iron beam. Two building scientists or engineers, scientists, somewhere in between, legacy of the Royal Society, right? They can go out and they can figure out just about anything. Hodgkinson and Fairbairn gradually develop a theory of beam performance in the 1820s and 1830s. And they do this first in cast iron beams, and then later they'll develop a theory using wrought iron beams. You can see that they are starting to grasp the mathematics of the shear moment diagram. So fish belly shape, but looking at where that fish belly shape has to sort of spring back up to handle the shear elements. They're looking at the lateral stability or the tendency of the beam to kind of rotate out from under its load. You can see in the beam plan, one of the lower flange is thicker in the middle because there's naturally going to be a tendency to have sort of secondary stresses because of torsion. So you also build a kind of moment diagram and plan to keep the beam in one place. And then look at the cross sections. The cross sections have these, the one on the left has equal flanges, the two others have unequal flanges. And this was Fairbairn's way of testing, seeing whether he could get at a working strength in tension and compression for cast iron. It turns out that cast iron is roughly 6 times as strong in compression as it is in tension, give or take. And if you look closely, you can see that the top flange, the one in compression, is about, say, 1/6 the area of the flange on the bottom. They test these to destruction, and they look to see which flange has failed first. And they know then that they can do the math backwards and figure out the working stress in tension or compression. They build these beams until they absolutely balance, right? Until the flanges fail at the same time. And that to them is the ideal beam in cast iron. Fairbairn puts this into practice. So here, Oral Mill in Manchester, cast iron beams sitting on cast iron columns. You can see that the proportion of the bottom flange to the top flange is 10 inches to 3.75. So taking advantage of cast iron's greater strength in compression, the top flange in compression is going to be smaller. And then also you can see kind of mediating between the desire to have a pure moment diagram, right, the most efficient structure possible, and the need to actually have a flat floor above. And so the longitudinal section is a sort of compromise between the ideal structural performance and the fact that we've actually got to get out there and build it, right? We've got to put stone tiles on top of this to actually make a floor. Now, rolled wrought iron, Fairbairn does a lot of work on as well, and you see here some of the shapes that he works with, arriving at basically what look to us today like pretty pure I-beams, right? The ones on the lower right are the latest ones where he's essentially figured it out. And he comes at this through both railroad construction. You see some of the sections that begin to get him toward that two-flanged I-beam on the left. It's a natural shape, of course, for a railroad rail. It has a bulb on top and the spiking flange on the bottom. But you can think of those two as if they were an I-beam. And the strength of locomotive rails are one of the things that leads them down the path to the modern I-beam. On the right, top right, these are deck beams for ship construction. And again, it's almost like you flip that around. You've got the bulb on the bottom now taking the tension, and the flange on the top that allows you to attach decking to it. Rolled wrought iron then begins to develop in shapes that are more and more useful. Here you see these guys pulling a channel shape out of the rollers in about 1830. By the 1830s, 1840s, we have all the families of iron shapes that we use today in steel, essentially. We have channels, we have I-beams, we have T's and angles. All of these are relatively easy to make with those hardened steel rollers. They take advantage of the ductility of iron at hot temperatures, but lower than melting. And they give you these reasonably precise surfaces that you can then drill and you can bolt to with confidence, right? Those flat surfaces are going to be reliable in ways that cast iron surfaces are not. Now, the real kind of test case for wrought iron, especially rolled wrought iron, is a bridge in Wales called the Britannia tubular bridge. And this is for a single rail, single locomotive and train that's going to go through it. Robert Stevenson, the engineer, takes advantage of this kind of developing theory of beam performance by designing the entire bridge like a giant tubular beam. If you look at the perspective section on the left, you see that there's a lot of iron in the top, a lot of iron in the bottom, and then there are enclosing walls on either side of the tracks. Those walls essentially serve as the web of the beam, right? It's a double web beam, and the flanges, top and bottom, are essentially doing the same thing that a flange in an I-beam does, right? So this is just a great big I-beam, but with the web split so that there's room for a train to go through it. You can see on a kind of micro scale, he takes the same principle, right? So those two flanges are actually made of little I-beams that are bolted together. The advantages to this are that it's a relatively lightweight structure, performs well in bending because it's got a lot of material far from the neutral axis of the tube, and he's able to construct these tubes on land, float them out to the piers, and as you see in the etching in the middle, to lift them up into place with cranes that are built on the towers themselves. So it also takes advantage of iron's potential for prefabrication. We see iron becoming really the way that engineers achieve long spans beginning around the turn of the century. And this occurs, again, mostly in Britain, but also in Northern Europe. Here is a market hall in Paris that is all prefabricated wrought iron units brought to the site, literally bolted together. Not only is iron much lighter weight, but it allows you to be much more efficient with your time on site. You're not waiting for mortar to cure or for stones to get set. You're able to kind of bolt things together, very much like an erector set, which lessens the amount of time that you have to have workmen on site. A lot of the prep work can get done in the factory, right? Things show up mostly pre-made, and it takes much less labor, much less effort to stitch them together on site. And you see, too, architects beginning to get inspired by this, right? We've seen this before. We get a new engineering development. It powers some fairly functional, fairly pragmatic structures to begin with. Architects come along and they see things in it that maybe pure engineers don't, and push the material in a slightly different direction. Here, 1814, early wrought and cast iron church. The piers are all cast iron. The arches are definitely wrought. And you can see that the architects here recognize that iron has a natural affinity to the kind of long, slender proportions of the Gothic. So they're going back 400 or 500 years for their aesthetic inspiration, but they're doing it with material that, of course, is very, very modern. There are, of course, super pragmatic buildings, though, and a lot of the kind of science of iron construction gets pushed by these. Trusses, in particular, become a very, very common way to deploy iron in long span construction. We've seen that Palladio, in his bridges, understood the basic principle of triangulation, but here we have a material in wrought iron that's really, really good in tension, can take much more loads with much, much smaller or thinner elements. And the drive to kind of make those as small as you can, to use as little material as you can. This is a great case of optimization. The theory of truss design develops when we get a material like wrought iron that can take tensile loads in enough quantities that it's kind of worth calculating, right? Seeing how much they can actually take. And even by the 1820s, we get trusses that are all mathematically correct, that we look at today and say, yep, that's exactly the way we would make a truss today, right, with the analytical tools that we have now. Super, super lightweight construction because you're parsing the compressive and the tensile zones of the truss. You're using the right material for the right force, so cast iron for compression on the top, wrought iron for tension on the bottom, and you're able to span with this very, very lightweight, very, very lacy element that can, again, be transported easily, can be knocked together on site in a very short period of time, picked up by a relatively small lifting device, and assembled by just a small labor crew up top. There are kind of architectural interpretations of these as well. This is a fish market in Hungerford, where you can see that the engineering really becomes the aesthetics. The moment connections between the cast iron columns and the wrought iron spanning frame above get turned into these kind of prototypical mushroom columns. That gives the building, of course, lateral stability in two directions, but it also becomes something that architecturally becomes a sort of theme for the building. And the trusses get kind of larger and larger, greater and greater spans, and find newer and newer uses. Here, naval slips in Portsmouth and elsewhere around the coast of Great Britain, where the roofs are taking on truss forms that match very clearly the kind of hulls of the ships. So showing not only the structural versatility of iron, but now also the geometric versatility. We'll take a quick break. The second half of the lecture will look at more examples of iron inspiring architecture, inspiring engineering, and giving the two a kind of place to talk to one another, where the structure is informing the architectural aspects of a building, but the architecture is also pushing back and kind of shaping the structure to its purposes as well.